Hi there, welcome to the Markforged live stream. We're here today in our Brooklyn Park, Minnesota office. Where behind me we have the entire Markforged suite of printers that we're going to get into. I'm Charlie Seitzer. I'm in additive sales here at Hawk Ridge for the upper Midwest, so I handle this territory. First, some housekeeping. There are some hyperlinks down below the video here. The first one you might see is the Eiger trial. That is the Markforged software that we're going to dig into here first in just a few minutes. The second would be to get a Markforged sample part. And third link available to you is a chance to win a 3D space mouse. So those are all below. You can click on those at any time during this broadcast. Also, there's going to be some Hawk Ridge Systems additive engineers in the chat. So when we're going through this live stream here, if a question pops up in your head, feel free to throw it out there. They'll answer some in the chat there. They'll also be pushing some to me on the iPad here as well. For those that don't know much about Hawk Ridge Systems, we have about 250 employees. We represent several different companies, the SolidWorks suite of CAD software, HP Jet Fusion printers, Markforged, which we'll get into, Artec 3D scanners, Materialize, which is additive software as well. And our role in the additive portion of this partnership is we sell the machines, we install them, and then we also do the service as well. So Hawk Ridge Systems has basically an end-to-end solution for our customers, starting with the CAD software, where you take your design idea, put it into motion there, which feeds the printer, and you get a part at the end of the day. We have numerous locations across North America, Canada, and the US, which you'll be able to see on the map on your screen. So if you lie in one of those regions, we're definitely excited to talk to you. So we're going to get into the Markforged printers here shortly. Markforged began about 6 years ago. They're based out of Boston. The creators, they had quite a bit of experience with the additive manufacturing technologies that were available at the time. Weren't that impressed, needed parts that were stronger, more resilient. And so they set out to change that, and what they came up with is the Markforged printers. And they've definitely added and become leaders in the plastics division as far as how much strength they can provide for the parts. I don't like to use the term disruptive too much, but they truly are a disruptive company in that they've added that strength and also brought a metal system that is office friendly to market. So I'd like to introduce Rob Stewart-Lean. He's our applications engineer and manager here at Hawk Ridge Systems. And you're going to start with the Markforged Eiger software first.
Yeah, we're going to do a quick look at Eiger. We're going to walk through the whole process basically. So we'll start with Eiger slicing software. We'll move on to the machines. We'll look at some parts. But let's start with Eiger here. So this is the first piece of it. This is the slicing software offered by Markforged for all of their systems. The same software is used for the metal machines or any of the composite machines, so it goes across the board. So let's start out here real quick. I've got this bracket piece I brought in. Orientation is really simple. I find a surface I want down, and I click on it, and it'll move that to my down surface. So if I wanted this to be my downward facing surface, it's just a highlight and click. So let's position it this way. Be my best spot for least amount of support, speed, everything else that I'd want out of this part. Now in the upper right corners here, there's a few little tabs. So my general tab, I have my material selection. So I can pick the onyx material, we'll talk about that a little later, the white nylon, or any of the metal materials. Since I have a metal system, I could select a metal and send it off to the metal machine. So for this purpose, let's go with onyx. I also have reinforcement material. So if I select this little pull down, it'll allow me to put carbon fiber or Kevlar or two different types of fiberglass inside that part to give it extra strength. This is a continuous fiber that's added inside as a strengthening device. So let's pick carbon fiber. Down here's my printer type. Since I have multiple materials and machines available to me, I'm going to pick the X7. So that's the machine I'm going to send my part to. If you notice, the table got bigger, so it represents the amount of size I have here. So if I go back up to the top, I have settings. This is where I can change my layer height. Right now it's locked in at 0.125 millimeters. Since I've selected carbon fiber, it'll lock me into that size. Depending on the model machine, you'll have different slice thicknesses available. On an X7, I can even go down to a 0.05 millimeter slice thickness. I also can set my units here or scale. If I want to make it smaller or bigger, I could scale it here. I have infill. So here's where I can pick what I want for my sparse interior. So I can take weight out of this part by making it not solid, but adding a sparse interior to it. I could pick triangular infill, I could pick a hexagon, I could pick a rectangular infill, or I could pick solid if that's what the part needed on it. So for this purpose, let's go with triangular. I have fill density. This is a slider that I can adjust how dense that pattern's going to be. So I can make it lighter or heavier depending on where I want to go just by sliding the slider back and forth. Roof and floor layers. How many solid layers do I have on the bottom facing surfaces? And how many solid layers do I have on the top facing surfaces? So right now I'm set at 4. If I were to take that up to say 8, I'll put 8 solid layers on top, 8 solid layers on the bottom. My wall layers is how many perimeter passes I'm making around the part. So right now with 2, I'm going to put 2 beads around the wall. A lot of times I'll select 4 here. If I'm going to ream a hole, I want it really accurate for a press fit. Let's say I'm going to put a heat stake insert in. I want a little more meat around that hole. I'll run it up to 4 contour layers around the outside. My last tab up here is reinforcement. When I look at this, this is where I'm going to be laying the carbon fiber that I've selected inside the part. So right now it's set for 8 layers. I can run this up or down from there even. What it'll do is it'll automatically put 4 layers of this carbon fiber fill on the bottom and 4 layers on the top. So I'll build a little bit of the onyx and then I'll lay 4 layers in there with carbon fiber reinforcement. If I run that up to 20, I'm going to put 10 on the bottom, 10 on the top. I also have the ability of going in there and changing any layer I want to add carbon fiber to or fill the thing, whatever. I can adjust that and I've got control of that. I also have 2 selections down here as an isotropic fiber infill and a concentric. So concentric means that I'd put the fiber just around the outside perimeter of the part. I can tell it how many beads I want of that. There's reasons why I do that if my force was in certain directions. Or in this case, we're going to pick isotropic just for demo purposes. This will put those perimeter passes around it, but it'll also fill the inside of the part with a bead of the carbon fiber or the Kevlar or whatever I'm putting in there. I've got selected down here 2 concentric fiber rings. So I'm going to put 2 on the outside. I'm going to fill the rest. The last piece down there is kind of interesting, the fiber angles. This is what it's going to do on each layer. So my first layer, my carbon fiber is going to be laid in there at 0 degrees. The next layer is going to go at 45. The next will go at 90. The next layer will go at 135. This creates almost a weave. So if you've played with carbon fiber, you know it's a fabric, kind of woven fabric. Here, by putting different angles at different layers, I can put fiber in there that'll give me strength in different directions. So if my force is different at different places in here, I can kind of distribute that force a little bit different. Once I have these set, I simply go into Save. If you notice, it's going to slice my part. It's going to determine where my roof and floor layers are, along with where my support is. After this, it'll figure out the tool pathing. Where's the head going to run in order to lay this bead of material down? And if you watch as this thing finishes, over on the left-hand side is my statistics on this part. So it'll come up here, give it a second to finish this little operation up. It'll give me my print time, 7 hours and 7 minutes at this part. My estimated cost of $11.26. Shows me my mass, how much plastic material I'm going to run, and how much of that continuous carbon fiber I'm going to use up. From here, I have 2 choices. I can either just hit print, send it directly to the printer, and I'm done. Or a lot of times I like to go into this internal view. It gives me an isotropic view here of my part. Now if you notice, the purple is the support material it's laid in order to support any overhangs. The blue that you're seeing in here is where the carbon fiber is laid. The white is the actual onyx or the base material that we're using. Now at the top here I have this 2D tab. When I flip that, it'll give me a top view of it. I can go into visibility, turn that on. This is my infill. And then using my right and left arrow keys on my keypad, you can see me going up through layers. So here's my carbon fiber in there at 45 degrees. The one just before it was at 0. So each layer you see a delta at 45 degrees. Then I'll cap that, and now you can see my internal structure on here. So this is the triangular infill pattern. It'll lay that in there, take weight out, takes time out, cost out. This will make a really strong part, you'd be surprised, especially when I'm putting carbon fiber in there, because I'm really giving it that extra punch with the carbon. Once I'm done with this, and if I like what I'm seeing, I'll just go to print. This will bring it up on my print bed. I can move this around wherever I'd want to put it on the bed. I can add other parts to this print bed. I could repeat this part, make multiples on the same bed. And then all I do is go down and hit print. It'll ask me if I want to add it to the queue or if I'd like to start the print. So what's interesting about this is if I have the machine prepped, ready to go, I can send this job to it without having any interface with the machine, and it'll start the job and run. So just this last weekend, I had a job that I couldn't get done before I left on Friday. I prepped the machine and got ready to go. Then when I got home later that night, I prepared my job. I sent the part. When I came in on Monday morning, the part was done, and I didn't need to come back to the office. It's kind of important, especially in today's world when we're looking at COVID and not having a lot of people in the office, that we can kind of keep that number down a bit. So really that's all there is to this, is preparing that file, setting the parameters you want, and sending it to the printer. So let's go take a look at the printer now. So if we come back here, this is the Markforged X7 printer. The build table on this is 13 inches by 10.6 by 7.9. So it's got a pretty good sized build area on here. Again, I can put multiple parts on there. I can build a big part, whatever I want to do to it. When we get a lot of questions about how office friendly is this is plugged into a standard 120 volt outlet on the wall. I've got a network cable to it so I can feed jobs to it, but it also is Wi-Fi capable. When you look at it, this one's actually running at this point. Very little noise. I have a cabinet underneath here. For those of you not familiar with fused filament systems, this is the most common system you'll find out there, invented about 30 years ago. This is a filament of, in this case, onyx. So it's a carbon fiber filled nylon material. It's fed up to the head. The head's heated and it extrudes a bead out. That bead's laid down on top of each other until we build this part up in 3 dimensions. I kind of like to tell everybody, remember when we were in 3rd grade and we did those pinch pots out of clay, you rolled the snakes and mounted them up? Yeah, it's just a high-tech way of doing the same thing we did when we were kids. When you look at the part up there running, there's 2 nozzles. So the rear nozzle is running the onyx material out of the box down below here. The second nozzle is feeding off this spool on the back left-hand side. If you notice, it says carbon fiber. So when I'm telling it where to put carbon fiber and when to put carbon fiber in the part, it'll move to that second nozzle and it'll feed off that filament spool in the back. That could be Kevlar, it could be fiberglass, it could be carbon fiber. The bed's prepared before a build with a simple glue stick. And when the parts are done, we basically just take a little scraper and we just pick them right off there. It's pretty simple.
Yeah, so not heated chamber.
Nope.
We could run it like this if we wanted to,
Right.
with the hood open. One of the questions we have here, what is the minimum wall thickness that you can print with the X7?
It's a good question. The bead on this is about 16 thousandths of an inch wide as it's laying it out. Since it likes to do a perimeter pass around the part, in theory we should have 32 thousandths because we're going to do a 16 and a 16. I've printed stuff smaller, thinner. You're kind of pushing the limit maybe a little, but it's amazing that it'll actually perform that way where it's actually laying material over top of each other.
Yeah.
So we generally try to keep that into that 30,000 range.
Right. So if you were going to change one of the continuous fiber filament spools out,
Yep.
say from this point, carbon fiber to Kevlar, kind of walk us through what that process is.
Yeah, so the process is really simple. We have a touch screen built into the printer.
Yep.
I'll go in and say change fiber material. It'll back the material out and allow me to wind that back on the spool. I'll go in and say load material. I'll stick a spool on. There's a small tube in the back that you can barely see in here. I'll fish it up through there. It goes into a drive wheel on the top, and I'll feed that over to the head and down through the nozzle. And maybe 3-4 minutes at tops, I've switched out to a different material.
Gotcha. And the X7 does come equipped with the laser.
Yeah.
It has a couple purposes to it.
Yep,
right?
there's a couple things. If you notice on the front here, there's a small laser mounted to the top. The main reason that I use it for is if I have to level a bed. If you've ever leveled a bed on a system, it's not real easy when you're doing it with shims. Here the laser will shine down on it. I'll run it through a head leveling program on the keyboard. It'll run through and scan the entire bed. It'll come back and pick the spot on the leveling feet, and it'll show me a bubble level. So all I have to do is reach underneath there and turn it and watch the level come to the middle.
Yep.
It'll also do a measurement at the beginning of a build and do an adaptive bed level. So if the bed's off a little bit, the head in relation to the table will compensate to make up that little bit of difference as it builds up and kind of levels itself.
Yeah.
The other use that we have for that is on Eiger, I can come in on a X7 system and I can tell it I want to do an inspection. So I'll tell it what layer I want it to pause on. The machine will pause, it'll run that laser over the part, and it'll map the dimensions of that part and bring it back on the screen. So I can compare what it's printing to what my actual drawing was or my part was, so I can kind of tell if I'm where I want to be, or if there's something not quite right.
Yeah.
It gives me that opportunity to say, hey, let's do something different here and start that again because something's not quite right on it. But it's fantastic because it'll give me that ability to inspect a part.
Yeah, that's great. Okay, let's talk about the materials real quick. So you kind of touched on it quickly, Rob. We start off with a base material, which is either the nylon white or the onyx.
Correct.
So let's start with the nylon.
All right, so this is the white nylon material. It's a base nylon 6 material, so it's very flexible. Where we use this on generally is we'll see this in like living hinges. We'll see this in anything that might have a snap fit, something that needs to flex but return a little bit. So this is a great material when we come to that. We see it being pretty abrasive resistant too. So I've seen these on conveyor systems as boxes come down or parts come down because it'll take that little bit of impact. So yeah, this is a great little material. The next one in the line is the onyx. So this is the same base material roughly, but it has a crushed carbon fiber inside of it, so it's infused in it. So what we saw on the X7 when we opened the box up was the onyx material and this black material. So if you look at this, just by adding that crushed carbon fiber into the filament, it increases my stiffness and strength. And this is different from the continuous fiber we're putting in with carbon fiber. A lot of times it gets kind of confusing that we talk about onyx with carbon fiber in it. We can go farther yet by adding even continuous carbon fiber inside of this stiffness to begin with.
Yeah, and this onyx is a stronger material than ABS. When we kind of look at additive manufacturing years past, you think of fragile parts, can't do much with it, but we're talking about functional parts here today.
Yeah, different world.
There's also an Onyx FR
Yep.
as well. So
Yep.
same material essentially with a VO rating.
Yep, for
Yep.
fire retardant.
Okay.
Yep.
So let's get into the continuous fiber filaments that they offer. The first one probably that all the buzz is about is carbon fiber.
Carbon fiber.
Yeah.
Everybody loves carbon fiber, right? You see it everywhere. Lightweight, strong. It's an incredible material. This is a continuous carbon fiber run inside this part. If you look at it, you can kind of see it's white. So this part was actually made with the white nylon. You remember how flexible that was? We've added carbon fiber in here. Now we kind of overkilled it a little bit. We've got a continuous fiber running concentric. And if you look at it, it's running completely through the part. But it increases that strength exponentially. We get carbon fiber in here in the right geometry, we can exceed aluminum strength that we'd see with an aluminum part like this. So this is an incredible addition to any part that you'd put in.
That's pretty important. That's a motorcycle brake handle, which we want it to be strong so that when we're trying to reduce our speed. We're not.
You certainly don't want that to break. That's a failure critical item on a bike.
All right. So Kevlar is the next one. Everyone knows kind of the most popular use or most popular thing about Kevlar.
Would that be bulletproof vest, right? Yes. Great material, strong. It gives a little bit. It's got some rebound to it. So this has got the same pattern as the carbon fiber one. It gives us incredible stiffness, but it also gives us that ability to rebound a little bit. So if we're using an application where we're taking some impact over and over and over, and we're afraid we might hit that carbon fiber hard enough to fracture the fiber inside the part, Kevlar is a great addition, instead of carbon fiber, because it'll take that impact and it'll give a little bit. So that's a great material. We run quite a bit of carbon fiber in Kevlar. And then lastly is this fiberglass. So we have two different fiberglasses. There's one that's a high strength, high temperature fiberglass, and then a standard fiberglass. This will help us increase the strength on it. It increases the heat deflection on the part slightly too. So this is a great alternative to the other two fibers.
Great. And so we have two more parts here that kind of show one, strength of carbon fiber, but also the kind of routing that we can do with continuous fiber. Yeah,
we look at this one. This is back to our base material, right? The white nylon.
Yep.
Very flexible. Now, when we're talking about adding carbon fiber to it, you notice this has got a concentric pattern running around the outside. It's extremely stiff. What's really interesting is when you look at it from the side, this has 4 layers of carbon fiber on the bottom and 4 layers on the top, and the rest of it is all sparse filled just like the other part. So when I look at this, with just that little addition to carbon fiber, I've increased that strength in this flexible part. So a lot of times there's no need to go in and fill this thing with carbon fiber. You could do it if you want, but it's extra money, extra time, and just adding 4 layers of each is giving us that strength. When we were talking too about sparse fills, right? Here's a good example of the interior part. So this has got that triangular infill pattern that we had on the part as I was processing an Eiger. So this takes a lot of weight out of the part. Gives us a lot of strength too. The pattern inside will kind of dictate that. I like the hexagon shape inside. Honeycombs are incredibly strong in nature. I can pick this just by selecting an Eiger what kind of a pattern I'd want inside the part. So I can take all this weight out, all this time of build out, all this cost out, and I can add carbon fiber to it if I want and give me strength in other spots. I like to laugh with, I've got some friends that are machinists. I ask them, could you machine that for me sometime?
Yeah.
And they just look at me funny, right?
Good luck.
So I can take weight out with that.
Yeah. So next, I think we're going to show one of the best features that Markforged designed is support removal. So a lot of times we do run into parts that need supports in them. And that's kind of always been, you want to avoid supports in an additive part.
Right.
I think Markforged did a great job of making it as easy as possible and quick as possible to get that part on the manufacturing production floor.
Right. So this part, the support material, is made from the same material as the model. Yep. So I don't have this switching back and forth of heads and all the time as I do a little layer of support. Have to switch back to the other nozzle, to the model. Switching back and forth is a lot of time. This stuff is accordion shaped on there. It peels right off the part. So all I have to do is just give it a pull, and I can strip my support material off from it. It's pretty simple. So when I look at this, I don't have any chemicals, I don't have any tanks. It tears off easily. If I produce this for the floor, I'm looking at, what we do there, about maybe 5 seconds. And I'm walking this out onto the production floor and putting this on whatever I'm using it for a fixture, an end-use part, whatever. So yeah, support removal is extremely easy here.
Good. All right, let's talk about this piece with some different hardware in it.
Yeah, we get a lot of questions with people wanting to print threads. Kind of goes back to your question, what's the thinnest wall we can do? What's the smallest feature we can do? I've printed bolts. To me, that's kind of silly. I can buy a bolt online for a couple cents. I can go down to the hardware store and buy that. And it's plastic, so it is what it is. So what we did here, though, is we made a little sample part to kind of show threads. So this is a 1/4 screw. My first hole here was actually a printed 1/4 thread. We drew in SolidWorks and printed that in there, and it functions just fine. My screw goes right in. The second one was a nominal hole for a tap. So I did 4 of those contours around the outside to give me a little meat, and then I just dropped a 1/4 tap through there. The third one over there is a press fit brass insert. Fantastic if you're looking for good holding force, won't wear out like plastic. It's a great application for using a press fit. The fourth one down here is a heat stake. If you've never done heat stake, it's really simple. I kind of go old school with it. I use a soldering iron. You're basically just heating the part up, putting pressure on it. It'll melt the plastic and it'll sink in there just like butter. What's nice about it is that plastic will then shrink around that knurling on the outside, and it gives you a lot of holding force. The last one's kind of unique. We see this with fused filament systems as a great advantage. This has a nut buried down inside of it. If you look at it from the back, you can't see the nut on the back. But if you get down inside there, you'd be able to see that there's a nut buried in there. So what we did is we printed this on the bed flat. We had the software pause at the top of the pocket. I went in and dropped the nut in and then told the machine resume where you left off. And it buries that part right down in there. So I've got all of the sides from that nut captive. So I got a lot of holding force in there using a captive nut from the inside, and it doesn't fall out. So if I'm doing something in assembly, I don't have to worry about holding nuts in while I'm trying to screw parts together.
Yeah, and it opens up the door, being able to pause it, put some hardware or something else in for a whole lot of different applications.
Yep, we see all kinds of stuff that gets buried inside of a part. It's kind of fun.
Yeah. So we're going to kind of get into the bread and butter of what Markforged does really well and where it's most commonly used. This is a set of soft jaws, jigs, fixtures. That's kind of all where Markforged has really excelled so far. So let's talk about this set.
Yeah, so if you notice, just a normal set of vise soft jaws. It's got a contour inside there. So what they've done here is, in the real world, when you're doing this with metals, you'd make these blanks. You'd go in there and machine out the profile of that valve that's in there. This would get mounted into a vise to hold valves in place while we do secondary operations on them, drilling, reaming, machining off surfaces, whatever. In this case, we did this out of plastic, using a 3D printer. This is being done everywhere. This is a fantastic application. So if you're using a holding fixture like this, it's simple. I draw the block in CAD. I take the CAD file of my valve or what I'm going to reduce out of it. I do a Boolean subtraction. So I just tell it, subtract part A from part B. It gives me this profile. I put that into Eiger, slice it, send it to the printer. I print my parts. It's a fantastic application. If I want more clamping force, I might add some fiberglass or carbon fiber into it if I'm going to need a lot of force on it this way.
Yeah, and I'd say the other thing, looking at this from an additive standpoint, this is not an overly complex set of jaws, right? It's fairly simple. This was printed just like you're holding it with the bed on the bottom, no support materials. They print it, they put it into use.
Exactly.
And for this use case, they were using aluminum, but they did this with onyx and fiberglass. So their cost from the traditional way went from $600 and some down to $50 for the set.
Exactly.
So
and taking no time off my machine shop. Those guys are valuable. They've got good work to do, right? They're making parts usually that are making money for the company.
Yeah.
So if I can take this kind of work off their hands, they're more productive producing the things that they're skilled to do rather than some of these things making their fixtures and jigs. So this is a fantastic application we see.
Yeah, and also the onyx material, non-marring for any metal application. So you don't have to worry about that causing any downstream effects.
Right. Yep.
Good. Let's talk about this CMM fixture we have here.
Yeah. So this little guy, holding fixtures, kind of similar to clamping, but a little bit different play on it. So the base plate is your normal CMM fixture for fixing up stuff you're going to measure or assemble. This part actually is made as one piece. So in a traditional way, each of these posts would have probably been machined. They're built out of some way and assembled into one piece. When I want to switch this fixture out, I'd have to bolt down each of the separate pieces and get them all aligned so that my part would fit back into my fixture and be able to clamp in to be able to do my measurements. So changing over a fixture for CMM printed when it's all one part by combining the others. Makes your changeover really fast. The other thing that's interesting is I can modify the shape of that holding fixture. So if there's a critical feature that I need to measure, I can open that spot up real easily in CAD, give me access to be able to make those measurements and not worry about how much machine time is that going to take in the mill to cut that away. And I'm not starting with a big block here and cutting and hogging away a bunch of material to throw away. This is printing just what I need and what I want.
Yeah. So if this would have started with multiple parts, it would have had to go through machining.
Yep.
And then to put this all together, welding, right? So we're taking out a couple different departments by just printing this very simple part, right?
Right. We're streamlining that whole production piece by taking out these steps and trying to get into everybody's schedules to get something done on time.
Right.
We're just punching it straight through the system.
So we have a bunch of different customers up in this area here. One of them in particular is using the Markforged composite printers to print end-of-arm tooling. So let's kind of talk about that use case real quick. They had a unique application, really, as far as what requirements this set of grips had to do. So let's talk about that.
Yeah, they had a very unique requirement. So they're using an end-of-arm tool for picking up these parts off their line, moving them through the assembly line. They came to us and said, we've got a requirement, though, that we're looking at a few 100 pounds of clamping pressure we need. And can we do that with plastic? We've been machining these things, and our turnaround times are slow. Can we speed that up? We want to be able to change this and do this faster and cheaper. So we looked at it and said, yeah, let's give that a shot. We took their design of their end-of-arm tool. We ran onyx because we've got stiffness there. We loaded it with some carbon fiber. We sent it to them.
And we felt really good.
I felt really good about it.
I did too.
I'm still looking at it going, you're asking this to do a lot, but I think we're pretty good. I think we're pretty close. So they ran it through testing and it performed really well, but they did have some issues with it. So we came back and we made a couple changes to it. We asked for some design changes. One, we changed some of the angles on the part so we could get more carbon fiber in areas in the direction of force that we needed. They had multiple directions of force. So we used some metal backing plates, simple things for them to cut, just blanks with holes to mount on the backside to give them some stiffness in the direction that we would not be able to get with the carbon fiber the way we laid it. And then they realized that Kevlar would maybe be a better solution to it because it has some rebound to it. Yeah. So when we're clamping with that kind of pressure, although this is all strong carbon fiber, we don't want to take a chance on those fibers in there failing at some point because of the pressure that they're putting on it. So Kevlar was better because it would give that little bit and then it would also return back to its shape that we wanted. Yeah. So yeah, they ended up putting those jaws on and clamping a few 100 pounds of pressure on that thing. It's just a fantastic story.
Yeah, it's a good story. We had to work quite a bit to understand exactly how to print this part in order for it to be effective over and over. I was there recently. The part is still in use. That's over a year and a half ago. They said 96% cost savings compared to how they traditionally would have gotten those types of parts that they printed in that last year and a half. So pretty impressive.
That's fun to hear that a year and a half later, that part's still functioning the way that we wanted it to. Yeah, that's fantastic.
Yeah. And we have another company in this area who is kind of taking the CMM fixture, but they kind of did it a different way. They put a fixture on a base, and they use that for assembling a part, and then they kind of moved it throughout their entire facility, right?
Right. So they did this thing that we tell everybody, right? You're going to buy the machine looking for that one thing that you're going to do. Yeah. And then as it's in-house, you start finding other things. So I believe their original part was as a CMM type fixture for holding and stuff for doing measurements. They realized that they could use that as a welding fixture too, and an assembly fixture. So this fixture that they've created, they actually assemble their parts on it. It moves into welding. All the parts are welded using that fixture. It moves on into measurement and metrology, so they can do all their measurements and specs off from it, and then it moves on to any other type of assembly that they'd have to do with it. And then they went one step farther. They said, okay, we got multiple versions of this product of different sizes. So let's make the fixture so we can use it for any one of those different products. So they've got this fixture that rolls through the plant. When it comes off the other end, the fixture goes back to the beginning of the line. They load up more parts. It goes on into welding, goes on into measuring, goes on into assembly, goes back again. Oh, we got different model.
Yep.
They mount those up. So they've grown as they've seen this, and they've started to use this in different ways than what they maybe were originally thinking.
Yeah, and we see that a lot.
We see that a lot.
One person starts and prints a part, another person says, hey, what's that part? And kind of brings it into what their area of expertise is. And
Yep.
use it.
I've seen places before where the engineering department gets it for prototypes. Machine shop figures out what this is. They start consuming more time on the machine than the engineering department does, and then they're fighting over their time, and they need 2-3 machines because they're finding these uses that they hadn't thought about. A lot of times we have people come to us with that silver bullet.
Yeah.
This is what if you can make it do this, I'll buy one. It's like, well, you don't understand that there's going to be hundreds of other things that you're going to find. That silver bullet's great, but look around your plant and see how many different places you could use something like this, and you'll find that it's just crazy.
Yeah.
The opportunities you're probably missing.
Yeah, lots of opportunities.
Yep.
All right, let's talk about the Metal X here. So
All right.
the Metal X has been shipping for quite a while, and it began to ship and installed at the beginning of 2019. And we've been included on a number of those that we've sold and installed. So let's start off kind of with the specs of the Metal X.
The basic specs. Yeah, so if you notice, it's about the same size as the X7,
Yep.
roughly. It's tabletop, desktop size. When we look at it, the bed in here is 11.8 by 8.7 by 7.1 inches. So although we have that size bed, we very seldom see a part made that large.
Mm-hmm.
Our sweet spot for parts in here is about the size of your fist to the tip of your thumb. If we're in that range, it's beautiful for that. What's nice is with the big bed is I can put multiple parts on there and build them at the same time. Mm-hmm. So it makes me more efficient as I move downstream into the next steps by having more parts to be able to run through the cycle at the same time. Part of the reason why we look at that size is if we look at these parts, they're made larger in Eiger. I don't have to design around that. What we're looking at though is the material in here is a metal powder with a binder in it. We're going to wash the binder away and then we're going to melt this thing into its final shape. So when I bring the part into Eiger in the size I drew it, I don't have to do anything to it. Eiger will automatically size this up like 18 to 20% when it's built to compensate for that shrinkage as it comes. So if I'm doing something the size of my fist, it's a perfect size for that size compensation. They've done a fantastic job kind of tuning this thing in to those sizes and that shrink.
Yeah, it's amazing that software that can run the plastics, it runs the Metal X and the entire ecosystem that they have.
Exactly, and similar to the other machine too, when we're talking about setup, this is a 120 volt outlet,
Mm-hmm.
network or Wi-Fi, sits in your office. There's nothing to it. Both printers are very, very similar in that way.
Yep. Yeah. Let's take a look at the spools.
Yeah, so up in here, our material's on the top in this one rather than on the bottom. If you notice, I have two spools up here. The one on the left is 17.4 stainless steel. That's what I have loaded in. The one on the right is a ceramic release material. So that spool of stainless steel is a powdered stainless steel that also has a wax binder and a plastic binder made into it to get it into that filament shape. The spool on the right, the ceramic, is used for support separation. So here too, when I'm building a part, I'm creating the support, I'm using the stainless steel as the support. But to get it off that stainless steel easily, it'll lay this ceramic material down between the actual model and the support. So when I'm done, it's basically mounting it in a vise, a wrap with a hammer, it pops right off, the ceramic breaks free, and my part comes off the model.
Yeah, and real quick, we discussed the changeover process for material on the X7. What's it like here if we wanted to go from 17.4 to an Inconel?
Yeah, pretty much the same thing. I'm going to go into my touch screen. I'm going to say unload material. It'll back the material out. I'll roll it up on the spool, take the spool out. I'll bring my Inconel in. I'll go into the screen and say load. It'll heat the tip up, allow me to get my filament down in there. It'll feed that through, purge the nozzle, and we're ready to go. Probably again, 5-10 minutes, I'm switched over to another material. So there's none of this switching of tips back and forth from material to material you see on some systems.
Yep.
This nozzle is small enough that it can purge that material right out of it and make the change of material very quick.
Yeah. And this is a somewhat heated chamber. It keeps the material a little bit warmer so that it's a little more pliable, right?
Yep. So when you look at this filament in there, it's a little brittle when it's cool because it's metal with plastic and wax. When we heat it up, it gets that flexibility to it so that it can actually feed off the spool without fracturing as it's building.
Yeah. All right, let's take a look at the print bed.
So when you look in here, this print bed uses a build sheet. It's vacuum sealed down onto the table. The part that's sitting on here we built a little bit ago, but it just kind of shows you the size of that build area to that part. It's all touch screen. There's a little set of brushes in the back to wipe the nozzles on this one. So in between layers, it'll go off every now and then and clean those nozzles off, and then come back and continue printing.
Okay, so Rob, there is a question here wanting to know about the Metal X system versus DMLS, direct metal laser sintering. Let's kind of talk about some of the differences there.
It's interesting because when you look at the older systems, that's been around for a long time of powdered metal, they're using a laser or an electron beam to melt that metal, actually sinter the powder into the part in the bed. That entire envelope is usually filled with argon gas or some inert gas. We know living in this area of the country what happens when you take a grain elevator, a lot of fine powder and a lot of energy. So you have to make that envelope inert so that we don't have oxygen in there. It's interesting too because every place I've gone, there's usually all the safety stuff around, right? They go through a safety training on, how to handle powders, how to not mix powders. Changing the machine over is really difficult to pulling one powder out and swapping another powder in compared to where we come in here and just load this thing up. When this part's done, I'm taking it out of here within a couple minutes. Part done, I'm good to go. In a powdered system, you're letting that cool over a period of time because there's so much energy and it's so hot that machine's basically tied up trying to get that energy out of it, cooling down to the point where I can go in and get my part.
Yeah.
The other thing that's interesting is we were talking about the ceramic support. When we look at that, I lay that ceramic layer down in there. When I go through my sintering process and stuff, it almost powderizes that ceramic. So when I whap this thing with a hammer, it breaks that ceramic barrier between the two and my part comes right off. Yeah. In powdered systems, we're basically building our support structure in and having to take that to a machine shop or somewhere and cutting the supports off it. So I've got the secondary operation, and I'm also involving my machine shop guys, which if I'm running a machine shop, I want those guys making money for me. They're highly skilled. Let's use them for the skills that they're trained for, not cutting support off from some part that I printed.
Yeah. And cost for DMLS systems would be around $1 million.
Yep.
And this is a tenth of that.
Yep.
Putting it in an explosion-proof room. So there's some serious considerations that need to be made.
I can tell you some stories, nothing bad, but it's like the safety that goes around those systems. There's a lot more that you're looking at than here. This, I'd stick this next to my desk in the office. I wouldn't worry about this print at all. Right. It's a little warm. It's actually kind of nice in the winter here in Minnesota. I have something like this in my cube.
Yep.
Keeps the cube area a little warmer.
Great. So let's talk about the materials I can print on the Metal X currently.
Yeah, so we've got a few different materials available here. First one is the stainless steel. So this was the first one that they came out with. This happens to be a part that I paused partway through so you can see the structure on the inside. So I can do the same thing as I do on the composite machine where I can lay a sparse filled interior inside this part. So this makes it nice because I'm taking weight out, I'm taking cost out. Again, my friends that are machinists, and I ask them to make me a metal part with a structure like that inside. They just look at me, but I like to play with them a little bit. So this gives me the ability to do that inside the part. I've also got a tool steel selection here available, an A2, a D2, and an H13 tool steel. So if I'm doing forming tools, that kind of stuff, where I'm running shears or bending tools, I'm gonna maybe run an A2 tool steel for that, or D2 or H13. Copper came out, this was maybe about 6-8 months ago?
Yep.
We've got copper. So if there's a need for copper parts, for heat sinks, that kind of stuff, if you look, this has got kind of a crazy shape to it. So you know that there's heat sinks out there that the geometry would be better for some heat dissipation, but they'd be hard to machine. In this case, I'm now able to freeform whatever shape I want. So my imagination can start to run wild on what kind of heat sinks I'd want and what kind of geometries. I've also got Inconel. So if you're not familiar with Inconel, the super alloy, this thing will take heat like nobody's business. If you've got a harsh environment, Inconel is like that material. So I can print Inconel just as easy as I can run stainless steel. So I've got a lot of materials available now. And they keep adding and adding. So they've got roadmaps of newer materials coming down the line.
Yeah. And the hardness as sintered is comparable to
a wrought.
What you get out of a wrought material.
Yep.
Okay, so after it's printed in the Metal X, it is in what they call a green state. So let's look at that part first.
Yep. So the green part, if you notice, it's not really green, it's gray.
Right.
But it's considered the green part. So this has the metal powder with the wax and with the plastic all built in it. So this is how it would come off the machine. If you notice, you can see that white layer in there maybe. That's that ceramic release layer to be able to get the part off from the support material easily. So this is considered green. It hasn't been washed and it hasn't been sintered yet. The final part we'd see like this. So my support structure is still stuck to that raft on the bottom. The part's separated easily, just pops right off. This is ready to go. When we look at, here's another example of something a little more complex down inside there, right? So this also had that ceramic release. We hit it with a hammer, it pops off. The other thing that you notice too is there is some more in here. I still need to pull, but all I gotta do is take and give that a little wrap. If I have a structure that might kind of encapsulate that a little bit inside there, Markforged has this thing called chunk support, where it'll break that into sections. So when I want to try to remove it, I can take it out in pieces as opposed to one big chunk that I might not have been able to get out of an opening.
Yeah. Okay, so kind of a good use case for this. This is a Stanley Black & Decker actuator housing.
Yep.
So this is a unique one. Obviously, people are going to look at this right away and immediately question the geometry of these holes, but that's also part of the story that makes this a great piece.
Really, these aren't like regular holes. No, they aren't. When we look at a fused filament system, this is one of the beauty that we have in it, is if I have an overhang, I need to put support there. In this case, if I do a 45-degree angle there, I don't have to put support under it. The fused filament systems are capable of laying these cantilevered 45-degree angles without needing support underneath them. So by changing their hole design to this, they eliminated the need for support. If you look at the part, that channel runs all the way around and out this side. If I had support material inside there, I'd probably have to use the chunk support to get it out of there. It'd be kind of difficult even to dig that out of there. So in this case, the design was changed so that they could run this with no support inside of it. What this thing's used for is it's an actuator assembly. So they've got a force being applied here, pressing on an actuator out a different direction. So this would be loaded with ball bearings. So when I press one side, it transfers that energy over to my plunger on the other side. So they don't have to be round. They could be any shape they want as long as they're controlling that ball. This other one is the same way. It'd be easy enough to get support out of there, but might not use the same advantage there.
Yeah, and this part originally consisted of 4 parts that they've made into one additive part. So it had the housing, a cover plate, 2 bolts to attach it. So they're reducing their reliance on different vendors to get these parts, and reducing assembly to get to a finished part.
Yeah, and this was like, if I remember right, one of them was a casted part, one was a machined part. So you've got different vendors that they're coming from most likely. And my alignment from one to the next, I don't worry about either because it's being built as one. So my assembly and how well I put this together kind of goes out the window because I can build it all as one part. And again, my friends that are machinists try to cut me this hole through there any other way. That's why it's multiple parts in the real world. So this took advantage of, no supports. It took advantage of internal channels and geometries that you couldn't make other ways easily, and combining multiple parts. So here they took all of these principles of design for additive and took advantage of all of them.
Yeah. Yeah, and that's one kind of similar example, a customer up in this area who's taking basically manufacturing tools, aids that they have in their plants, and which typically were made of two different parts, two different types of materials, printing it in one. So they're reducing their supply chain, basically. They're shrinking that, which sometimes that doesn't mesh up really. It might be on different schedules. You might be waiting for a part just to finish to get to your end part.
Yep.
But
And in today's world with COVID, if you've got two different vendors, one's shut down for a couple weeks, and now you need both parts to make this, but one can't supply as quick as the other. And then about the time, you know how it goes, this guy starts delivering, this guy will shut down. So now I'm bringing it all in-house, and I'm making them as one part, so I don't have two boxes on the shelf of inventory to try to balance. I have one.
Yeah.
And if you do it here where there's 4 different pieces, now think of my inventory of trying to balance 4 separate items as opposed to balancing just one on my inventory line.
Yeah. So real quick, let's talk about what would be ideal and not ideal geometries and kind of applications for the Metal X.
Yeah, so metal, what I look at is if I've got a place that's getting sand casted parts, stuff from a foundry, investment casting parts, if they've got a machine shop and they're doing some low run production of stuff, could be prototypes, could be production parts.
Yeah.
But when we get into that lower volume, kind of custom one-offs even, or low level production, you're gonna see that in here. So these parts, when they're done, they're machinable. You can drill them, you can tap them. So if you had a sand casted part, you're going to bring it into your machine shop and do a secondary op on a couple places, touch off the places that are critical. We're in the same boat. Why not print it and not have this big chunk of metal that you're cutting away and throwing away? The machine shop too, you look at it, a lot of times the machine shop is your bottleneck. Those guys are always busy. They're kind of the linchpin to the whole system.
Yeah.
If I can take some weight off them, it's all the better. So if I can print them apart and all they have to do is touch off a couple places on it rather than machining that from scratch, my machine shop, starts to open up its production.
Makes more money.
Frees it up, makes you more money.
So lastly, let's talk about the holy grail of Markforged parts. This is what we call a hybrid part, metal and composite.
Yep, so here we've combined both technologies together. This insert is a stainless steel part coming off the Metal X machine, similar to what you'd find in, say, a socket set. So we have the bit that we want to change out for different sizes, or this might be a high wear item. So we're going to print this out of metal. We're going to put it into a composite handle. So when got to get them to line up there. When I build this, I'm going to build this one on the composite machine with onyx and with carbon fiber inside of it. This gives me the stiffness. It reduces weight. I can reuse this multiple times with different bits in it. And I've taken all that mass out of it, all that speed out of it. So it's interchangeable, and I'm actually taking advantage of 2 different technologies here.
Yeah.
2 different types of materials.
And you customize the handle if you wanted to for a bigger hand, smaller hand. It's lighter weight than a metal handle would be, a stainless handle. Yep. So might be some benefits there.
Yeah, we see times, with different customer stuff with repetitive motion injuries. Mm-hmm. So when you can take weight out, or you can customize the handle to the operator's hand, you can change the angle on it. Mm-hmm. There's a lot of that stuff that you walk into a shop once they've been playing with the machines a bit, and they go, oh, there's these other opportunities in here to kind of help with these other things that are going on. Never would have thought about it, and without a machine, they would have never explored it.
Yeah. Okay, so to get to a fully sintered metal part, there's 3 steps here. We print it, and then let's take a look at the wash.
Yep. So when we're done printing, we already kind of went through this, right? We're going to print the part. We've got this green part. I'd take my part out and I'd go to this wash station. If you kind of get a shot down in there, this is a wash station. It's using Optium Cyan industrial degreasing chemical in there. I'm going to raise that basket up. I'm going to put my green part in it. I'm going to submerge it down in the tank. That will dissolve away or work out the wax material out of that part. After it's soaked long enough, I'm going to pull it out of there and I'm going to move it over into my drying spot where my parts are going to sit and dry and get that optium scion out of them. Now this is considered a brown part. So I've now taken the wax binder out of it. I've still got the same part, same size. It's just now has the binder removed from it. From here, I'd take my part and I'd go over to the sinter. I'd open up my little door on the side here. Gives me into my cavity for my sinter. If I reach back in there, I have a plate that has the parts that I'd finished yesterday. So these are finished stainless steel parts, ready to come off the raft. Now I'd take my brown part, put it back on there. I'd slide that back into my sinter, all the way in. Then I have this heat shield. It's going to make kind of some weird noise here. See we don't freak you out too much. So that'll go in, this will close, and I'll bolt this down, seal up the chamber. From there I come to the front and hit Start Sinter. It'll ask me a few questions. It'll say, what kind of material did you put in there? If you notice, the raft actually has it printed. It's got an S on there telling me they're stainless steel. So if it's copper, I'd have a different logo on it. I'd put the parts in. I start the sinter up. It'll ask me what material. I say stainless steel. It'll walk me through a set of menus to check my gas panels and stuff. It'll go through a test of valves and things to make sure everything's functioning right. And then it'll start into its heat profile. So what's nice with the system is it's all tied together. Yep. It's all designed as one. The printing, the size increase that's done in Eiger, right to the printer. The wash system, Eiger tells me how long it should wash. Yep. I measure my green part for weight. I measure the brown one for weight, so I can tell how much has been reduced from it. When I hit that certain percentage, I know it's ready and that the wax is gone from it and it can come in here. Yeah. So everything's tied together.
And so each material has a separate profile on here, a little bit different in how it ramps up the heat and brings it back down. Time is going to vary just a little bit, not much. But we're looking at, this will vary based on the volume of the part that's in there. The sinter cycle is about 24 hours.
About 24 hours, yeah.
And we have the Sinter 1 here in our Broken Park facility. There's also Sinter 2 that started shipping at the beginning of this year, which is a bigger system, handles more, it's more than double the volume that you can sinter at a time. Yep. And a little more effective per run.
Right. And that's why, you know, when we look at the size of the print bed, if I print 10 parts on there, I wash them all together. If they'll all fit in the sinter, I can run this real efficient by rather than onesie twosies. Yeah.
So or you can batch.
You batch them. Yep. Yep.
Okay. So also included is the gas panel that's behind you.
Yeah.
So let's talk about that real quickly because the gas tanks are here.
Yeah. The octopus back here, I guess we call it, right? So this is the gas panel supplied by Markforged for the sinter. As you can see, it has all of its own regulators and gauges on it. What we're doing here is we're bringing in an argon gas and a mixed gas of argon and hydrogen. So my tanks you see on the side over here, this is a 6-pack of argon gas. You can do a Dewar tank in here that has all the gas in it. It's a little more efficient. If you're running a lot of production, it's the way I'd go. Since we run benchmarks in here and we'll run a part here and there, this is much more effective for us. So we've run this at 6 tanks of argon fed into the panel, and then there's a spare bottle. So if this goes empty, it knows enough that there's a full bottle here, it'll switch over and keep on sintering with that extra argon in there. Yeah. The machine will tell me where my pressures are and if I have enough gas to finish the cycle before I start. So they've kind of bulletproofed the thing. Yeah. And then I've got my 2 mixed gas here. So it'll go from one tank, when it goes empty, it'll switch to the other tank, allow me to swap a tank out, and just keep these things going. The panel talks to the printer, or the sinter, I should say. So the 2 of them are constantly communicating. So when I start a job, the panel knows what kind of pressure it has and tells the sinter of them where we're at.
Yeah, so this looks pretty complicated. And at the beginning, I did mention we we do the installation as well. The Metal X, we do the installs for. Kind of walk us through what a typical install would be for a customer for a Metal X.
Yeah, an install on this system's about a week by the time we get done with it. What's required is the ventilation being put in, the fans. There's one for the Sinter, there's one for the wash station. Those need to be installed, ready to go. We require that the gas panel be hung. There's a template to be able to mount that. It shows the height and locations and all of the stuff that you need to know where to put that. And then you'll pull your printer out of the box, have it ready to go, your Sinter on a table. Our guys will show up. They'll generally, I believe, start on the Sinter is how I like to do them, because there's a bunch of calibrations here.
Yeah.
So they'll run the gas lines, and then they have to go through a heat up series on it. And then they run a set of sample parts through it just to get everything here checked out. It's not really tuning, it's more running tests to make sure that everything's working on it. Yeah. And while this is sitting and running, then they're setting Optium Scion into the wash tank. They're setting up the printer, and then they start through all of the training.
So teaching the users how to operate the entire system. Teaching them how to use Eiger, what to look for, a little bit as far as what you can do and what you can't do with parts, mins and maxes.
Right. Yep. So they'll start with Eiger. They'll walk the whole system through for them.
Yeah.
So yeah, when it installs about 4 to 5 days. I'd say 5 days on the safe side.
Yeah. So it really is amazing. This is an office-friendly system. On the other side of this wall is a small hallway, and on the other side of that is our offices, which we sit next to, and I feel comfortable.
Oh, yeah.
You feel comfortable?
We wouldn't put you at risk, Charlie, so of course not.
We're doing okay.
You're way too valuable for that.
Good. So another question came in, Rob, what safety equipment is needed to operate the Metal X system? So printer, wash, Sinter.
Yep. Good question. Really, the printer could sit in your desk next to you. There's nothing there, really. Completely safe. It's just like having a little box
printer
with a little heater and a 2D printer sitting next to you. The wash station's probably the biggest one. Rubber gloves, goggles. The Optium Scion is a degreasing agent, so it is a chemical. There's cooling coils around it, so when I open the top up on it, the cooling coils keep the vapors from coming out. So I don't have to worry about respirator necessarily. I'm not going to put my head down in there. But goggles, gloves, apron, those types of things, so you don't get it on you.
Yeah.
The Sinter, set of gloves probably isn't bad. When this thing's done sintering, it'll cool down. It'll get to the point where it won't let you open up the door. It'll tell you you're still too hot to open.
Yeah.
So when it's giving me the okay, I open it up. It might still be warm in there. They suggest some gloves, but if it's been sitting long enough, it's cooled down to room temperature anyway. So there's really nothing to it. Even to the touch when this thing's running, it's not like it's hot.
Right.
It's all insulated.
Right. Yeah, that's good. So that's a really good summary of the entire Metal X system, along with their materials and the X7 as well. So thanks, Rob, for that. If you have questions at this time, you can still put them into the chat. Our engineers are still there answering the questions, and we'll be on there for a little bit longer. There's still time to win the 3D Space Mouse, so the link's below. You can do that. Also, to get a trial version of the Eiger software, so you can put your own STLs in. You can orientate the parts. You can include carbon fiber. You can leave carbon fiber out. That's all available to you, as well as requesting a sample part from us. So those links are still live. You can do that there. If you need to talk to Hawkridge Systems salesperson or engineer, we are here. You can find us on the website on the Contact Us page, and you'll get routed to the right person in your area. If you're in the upper Midwest, it's going to be us. Yeah,
we're it.
So that'll be good. Yeah, that's right. So thank you for joining us today. We're out of time, it looks like. But we filled our time, so that's good.
That's good.
Thanks, Rob. Thanks to Markforged. We're really happy selling and installing and servicing this and helping our customers, so we really appreciate it. Have a great day.